Hey there, welcome to the AP Statistics Quideo number 5. Today we'll start with the basic question. So the basic question looks at estimates of the daily intakes of calcium in milligrams for 38 women who were tested who were between the ages of 18 and 24, and they participated in this study. So in the table they give you the daily calcium intakes in milligrams, and they want you to work with those numbers and try to work out the problems. So the first part says display the data using a histogram and then describe the distribution. So I took the liberty of graphing out a histogram. Remember, a histogram has to have all the bars touching each other, and they're displayed in ranges. So, for example, the x-axis, the explanatory variable is the calcium intake in hundreds of milligrams. So 3 to 5, 5 to 7, 7 to 9, all in hundreds of milligrams. And then the y-axis is the frequency. So how many of each one of those ranges actually is present. So as you can see, here's a histogram, but we're also going to be doing a distribution. We're going to be describing the distribution rather, and for that we need to do SOCs. So S being our shape, it's fairly normal, but it's actually slightly skewed to the right because you see this little dip and little tail here of the values that you have your potential outliers up here, which brings us into O, which is your outliers. You have potential ones at 1,933 and 2,433 milligrams of calcium. Then you have your center. So because this is skewed, you might want to use your median, which is 845 milligrams, but you could also look at your mean just to see that it definitely is skewed right because it's 926, so it's going to be closer over here, whereas your median is going to be closer over here. Lastly, you're going to use the spread. So for this spread, you could say that the spread is about 505 for your interquartile range, so between Q3 minus Q1, or you have a standard deviation of about 427. So either way, you could say that it's fairly variable. It spreads all the way from around 300 to all the way around 2400. Those are all things you would say about the spread, but that's how you describe the sampling distribution. Okay, next let's look at part B. So part B says calculate the mean, standard deviation, and standard error of the data we're given. So first let's start with the mean. Now the mean is going to be the sum of all the values divided by the n, or to put it easier, you can just use your calculator and just go to stat, edit, enter in all your values like I did in list 1, and then you quit. Go back to stat and go to calc and one variable statistics and put it in your L1 values. And then you have your mean at the top, your X bar, which in this case we're going to find is 926.026. Your standard deviation, your S of X, which is 427.2295. So those are the two values, mean and standard deviation. But then they also want you to find your standard error, which in any case, using a mean, the standard error is equal to the standard deviation divided by the square root of n, or the square root of the number of values you have. So in this case, it's the 427.2295 divided by the square root of n, or square root of 38, to get us a standard error of 69.306 milligrams. So yeah, all these values are in milligrams. Just remember the 926 for the mean, the 427 for the standard deviation, and the 69 for the standard error. Alright, so part C asks us to find a 95% confidence interval for the mean. So for the confidence interval, whenever you're being asked to find one of those, you want to use PANTS. So let's start with P. P is your parameter. And in this case, P is the mean daily calcium intake in milligrams for the women tested between ages 18 and 24. But because it's because it's the parameter, it applies to the whole population. Remember P for parameter and population. So it actually is not just the women tested, but is in fact the entire population of women 18 to 24 and their daily calcium intake. So then we go to A. So A, we're going to assume independence and assume that the general population of women 18 to 24 is over 380. So that's good. We can definitely assume that's true. Assume that an SRS of women is taken. They don't explicitly tell us that, but we have to assume that in order to proceed with the confidence interval calculations. And assume normality. So our n value is 38, but as we found in part A, there's not really any major skew. There's like 1 or 2 outliers that aren't really all that significant. They're not going to really change your data that much, and because we have such a high n value of 38, we can go ahead and proceed with caution, but proceed with the calculation anyway. Okay, so then we're going to get to n, which is name the test. So in this case, we're using a one sample t interval. So the formula for the one sample t interval is X bar, or your mean, plus or minus T star times your standard error, or your standard deviation divided by the square root of n. So in this case, you have 38 samples where n is 38, and in order to find your degrees of freedom for that, you're going to do n minus 1, or 38 minus 1 is 37. So then you pull out table C in your book, and you go over to, okay, well, 30 is the closest one we have because you have to go down, and you scroll over to 95% confidence, and you find your t-star of 2.042. So then use that for your t-star. Your degrees of freedom you use is 30, and we calculated the mean and standard error above. So then you just plug everything into your equation right here, and you end up with 926.0263 plus or minus 141.5224. Then you add and subtract those to get your full range, and your confidence interval is 784.5039 to 1067.5487. So now you have your confidence interval calculated. You made the assumptions to do it so properly. Now all you're left with is making a statement, your S part of PANTS. In this case, you can say with 95% confidence that the true mean calcium intake in milligrams for women 18 to 24 is between 784.5039 milligrams and 1067.5487 milligrams. Okay, so the final part of the basic question says to eliminate the two largest values and recommend the 95% confidence interval. And what do you notice? So we're going to go back, and we're going to go to our calculator, and we're going to go back to stat, edit, and we're going to go, and what I did was I took list 2, copy list 1, but took out the two largest values, so the one around 1933 and 2433. And then I'm going to go to stat, calc, and go back to one variable statistics, but I'm actually going to put in list 2 this time to get my new mean and standard deviation. So I have a new mean of 856.1944 and standard deviation of 306.7296. So I wrote those down there, and I'm going to do the same exact thing. So in this case, our parameter is the same as it was before. It's the mean daily calcium intake for women 18 to 24 years old, and the assumptions A are also the same. You assume independence. In this case, the population is over 360 because your n value is only 36 now because you took out two values. You're going to assume SRS, simple random sample, just as you did before. No reason to change that. And you also assume normality because once you take out those two outlier values, if you remember going back to the histogram from part 1, you actually eliminate these two values right there, and your histogram looks a lot more normal. So you can definitely assume normality again. So then you go to n, your one sample t interval, just as was before, same formula, and because you only took off two values from your n, you can still use the same degrees of freedom that I showed you in the book. So it's still a 30 degree of freedom problem. So then you have a t-star still of 2.042. So then you use the same formula, and then different mean and standard deviation, plug it in, and you get this interval of 751.8040 to 960.5847. So as you can see, the confidence interval is smaller. It's smaller, and it's also on the lower end for both sides. And that's only because really you took out those two outlier values. Because you took those out, the data is more condensed. There's less variation, and as a result, you have a smaller interval that you can say with the same confidence that it's going to be within that range. So our final statement for this is that we are 95% confident that the true mean calcium intake for women 18 to 24 is between 751.8040 milligrams and 968.5847 milligrams. And remember, as I said before, we really noticed that once we take off these two outliers, the variability in our data becomes lowers. So 95% confidence interval, the same confidence as we had before, provides us with a smaller margin of error, which in this case it's only 104 as it was 141 the last time, just because we took off those two values on top. So it's a smaller interval, same confidence. Okay, so next we're looking at the advanced question. Now the advanced question says you play two games against the same opponent. The probability that you win the first game is 0.4, the probability that you win the second game given you win the first game is 0.2, and if you lose the first game, the probability that you win the second game is 0.3. So the first part of this question asks if they're independent. And we can simply say that these are not independent because the probability of you winning the second game is dependent on the probability of you winning the first. So if you win the first, your probability is lower than if you lose the first. So because the probability doesn't remain the same throughout, whether or not, however your first game turns out, they are not independent because, in fact, the two events are dependent upon each other to determine what the probability is going forward. Okay, so next, part B asks what the probability is that you lose both games, and part C asks what's the probability that you win both games. So the probability that you lose both games, let's start by looking at the probability that you lose the first game. So it tells you if you win the first, or the probability that you win the first game is 0.4. So the probability that you lose the first game is the complement of the probability that you win the first game. So it's the probability of 1 minus 0.4, or 0.6. Then the probability that you lose the second game, given that you lost the first game, is going to be the probability of 1 minus 0.3, or 0.7. So when you have combined probabilities like this, you have to do these joint probabilities. So the probability of A and the probability of B given A. So 0.7, your first one, times 0.6, your second one, to get you an overall probability of losing both games of 0.42. Now part C asks us to say what's the probability of you winning both games. So the probability of you winning the first game, as I said in the problem, is 0.4, and the probability of you winning the second game, given that you won the first game, is 0.2. So those are explicitly stated in the instructions. So then in order to find the probability that you win both game 1 and game 2, you have to multiply those probabilities, as it says here, probability of A and B given A. So 0.4 times 0.2 gets you 0.08. So then part D asks you to construct a probability model for X, where X is the number of games you win. So you can either win 0 games, 1 game, or 2 games, depending on how you do. So the probability that you win 0 games or you lose both is given in part B that we found 0.42. The probability that you win both games, you win 2 games, is 0.08 as found in part C. And because we know that you can either win 0, 1, or 2, we can add those together and get 0.5, and then know that 1 minus 0.5 is going to be the probability that you win 1 game, so it's 0.5. Or you can do it this way and find if you lose the first game, that's a 60% chance, 0.6, and win the second game, it's a 0.3. That's the probability. Multiply those together to get 0.18. Or the other way you could win 1 game is win the first and lose the second, so 0.4 times 1 minus 0.2 to get 0.32. Now if you add those together, you find you get 0.5 either way. So either way works, you get 0.5 for your probability of winning 1 game. Next, we're going to look at part E. It asks you to find the expected value and standard deviation of these probabilities. So the expected value is simply your X times the probability of X for each one, and you add the sum of all of those up. So it's 0 times 0.42 plus 1 times 0.5 plus 2 times 0.08. As simple as that, you just multiply, and add the sums or add the products together, and you get a 0.66. So if you were to play at any point in repeated trials, you would expect to get 0.66 games. You'd expect to win 0.66 games on average over time. So that's not all that good. And then next it asks you to find the standard deviation. So the standard deviation formula is X minus mean squared over the probability of getting that X. So in this case, we could start by saying 0 minus 0.66 squared times the probability of getting that, so 0.42, and then you add all those and take the square root of it. So once you plug in everything, you get 0.62. So that's a pretty moderate standard deviation of 0.62 in this case. But yeah, that's your mean, or your expected value, which is kind of serves as your mean in these problems, and your standard deviation of your expected value. Okay, lastly, we're going to look at the AP question. So the AP question looks at a U.S. Department of Agriculture investigation that uses 2 methods to determine the level of E. coli bacteria in beef. So they used method A and method B, and they want to find out if there's really a difference in how much E. coli is calculated, or how much E. coli is found in millimicrobes per liter of ground beef. So the main question, the only question in this case, is there a significant difference in the mean amount of E. coli bacteria detected in the 2 methods of beef? So you need to provide, in 2 methods of testing beef, so you need to provide statistical evidence to prove that. So in this case, they ask for statistical evidence to prove something. And the immediate thing you should think is phantoms. So you start and you write out your hypotheses. So your hypothesis is that the mean difference is going to be 0, that's your null hypothesis, and your alternative hypothesis is going to be that the mean difference is not 0, where the mean difference is the mean difference between method A and B in the level of E. coli bacteria contamination found in the beef by the 2 different methods. So that's your parameter, that's your P, that's your H over there. And to start, I want to go ahead and put all these data into the stat. So I put L3 as your first of your method A and L4 as method B, but because these are matched pairs, we're actually going to make it L5, which is the difference between L1 or L3 and L4, or the 2 different types. And then we're going to go to stat calc one variable statistics and go to L5 and get all our information for that. So our mean is 0.29 and our standard deviation is 0.6297. So I went ahead and wrote that down here for everything, and n is going to be equal to 10 because that's how many pairs we have. But next we're going to go to our assumptions. We're assuming an SRS, but that's actually given to us, so we don't really need to assume it, it's just part of the process. We're also assuming independence because the specimens are randomly and individually selected. We can assume that they're not going to be interfering with each other and impacting how the other ones play out as far as how much is calculated and how much is found of the E. coli in each one. And then lastly, we're going to assume normality. So in this case, I took the liberty of making a little histogram, which is actually pretty perfectly normal. And even though there's only a small sample of 10, we can assume going forward that it's normal, but we would like to proceed with caution just because of such a small sample size. Lastly, I want to point out our degrees of freedom in this case is 9, because our sample is 10, so 10 minus 1 is 9, and our alpha value is 0.05. We're looking with 95% confidence for the statistical calculation. So next, we're going to be looking at a one sample matched pairs t-test. So that's the end part where you're going to be naming the test. And here's our t where we're going to be solving. So t is equal to the mean difference minus the expected or the assumed mean, which is going to be 0, over the standard deviation over the square root of n, or your standard error. So as I said before, we found these using our calculator, and we're going to plug it into the formula and find a t-value of 1.4563. Now, because it's a two-sided test, because it says does not equal, we're actually, when we go into the book in a second, we're going to multiply whatever probability we get by 2, because remember, you can fail on either the positive or the negative side, because it is a not equals rather than a greater than or less than. So as I said, we have a degrees of freedom of 9, and we're looking for a value of 1.4 around there. So immediately like you hear, so it's 1.38 to 1.83, your 1.4 is going to fall in between there. So p is going to be in between 0.05 and 0.10. But as I said before, you have to multiply that probability by 2. So then you get a probability of 0.1 to 0.2. Now you can check this on your calculator. You go into stat, tests, and you do a t-test, and you can go to data and put in L5 and make sure it's not equal to, and calculate. And your p-value you get is 0.179. Now if you notice, you have the same mean, same standard deviation, same t-value, so you know it's all right. N is equal to 10. So our actual p-value is going to be equal to 0.1792. So then lastly, you're going to go to your M and your S, where M is your make a statement and S is write out that statement. So we are going to fail to reject the null hypothesis. So specifically, we're going to fail to reject the null hypothesis that the mean difference between methods A and B in the level of E. coli bacteria contamination found in the beef between the two methods is going to be 0. We're failing to reject that the mean is 0. So basically, we're saying that we don't have enough evidence to disprove the fact that these two mean differences, or these two mean calculations and findings in the bacteria are the same. So we failed to reject because we found a p-value of 0.1792, which is greater than our alpha value of 0.05. So because we found a p-value greater than our alpha value, we failed to reject the null hypothesis, and therefore we do not have enough evidence to prove that there is a difference between the two methods of calculating E. coli, or finding the E. coli in the beef.